We conceived a neurorobotic platform to study the encoding of leg muscle activation in the subthalamic nucleus of patients with Parkinson's disease. Participants were instructed to perform an isometric knee joint extension task while sitting comfortably. We recorded the local field potentials from the STN associated with these movements, either through externalized DBS leads or using the sensing capabilities of a last-generation implantable stimulator. During the task, local field potentials exhibited modulations both in low and high beta power, which were aligned to the activation of the quadricep muscles. Performing the same task with a bigger force did not induce changes in the modulations recorded in STN signals. We then instructed participants to perform the same task, but to sustain the knee extension push for 5 seconds. STN signals exhibited clear modulations at the initiation and at the termination of muscle activation. Performing the same task with a stronger force induced similar modulations, but delayed the resynchronization of beta power. These results opened the possibility to decode the level of leg force in real time from STN local field potentials. We developed classification algorithms that acquired and processed LFP continuously and generated predictions of 1 in 3 states: rest, weak force, or strong force. At each time, the algorithms generated a prediction for these 3 states based on the entire power spectrum of bilateral LFP. We then evaluated the performance of these algorithms during real-time experiments. 3 patients performed the task in real time. Upon initiating the task, the probability of weak force became dominant. The same happened for the strong force as soon as the participant was required to sustain a high level of force. During the release of the effort, the decoder progressively predicted weak force and finally rest. The same performance was achieved on the other patients.